Hi, this is Professor Stugard, and in this video we're going to talk a little bit more about surfaces. So, our first definition, the trace of a graph in R3 is going to be the intersection of that graph or surface with a single plane. Now, if that trace is a cross-section of the graph when it's sliced by a coordinate plane, we call that a projection. So again, basically think of some surface in 3 space, you're slicing it with like a piece of paper and seeing what it would look like on that piece of paper. And again, if it's in a coordinate plane, it's called a projection. Otherwise, the more general term is just a trace. So let's take a look at our first example. Let's say I want to find the trace of the sphere given by the quantity x minus 1 squared plus the quantity y plus 2 squared plus the quantity z minus 7 squared equals 25 into the plane given by z equals 9. So again, before we start trying to do any math, it's going to be a good idea to make sure we understand what the problem's actually talking about first. And that's going to mean understanding the surfaces involved and what's going on before we actually start trying to do any math. And you're going to see that theme continue where, again, particularly as we do higher level math, we need to spend more time thinking about the problem before we really dive in. Well, to talk more about what's going on, well, I know I have a sphere, right? This is the equation of a sphere. We're told it's a sphere, but hopefully we can just see that anyway. And we see that its center is going to be at the ordered triple, 1, negative 2, 7. And it has a radius of the square root of 25, which is just 5. And so again, remember, it was a while back that we talked about, well, spheres back in one of our first videos. But again, remember, it was always taking the square root of that number on the other side because it was that radius squared. Now, the plane z equals 9 is, again, just that plane surface where every ordered pair, or sorry, every ordered triplet has 9 for that z component. I can graph these as well. Again, I used GeoGebra, the GeoGebra 3D grapher. Feel free to use that yourself too. Obviously, it's free and easily to find online. And so the intersection, where the plane and the sphere intersect each other, that intersection is going to be my trace. And so we can kind of see here from, again, looking at this in 3D, that looks like that intersection or that trace kind of looks definitely circle-ish. And let's see if we're actually right here. So to do the math, this was actually pretty simple. I'm just going to substitute z equals 9 into that equation of the sphere, which means I keep everything the same. Again, I'm just replacing the z with the number 9. And now trying to simplify. Well, 9 minus 7 is 2. 2 squared is 4. And if I subtract 4 from both sides, now I have x minus 1 quantity squared plus y plus 2 quantity squared equals 21. And now, because I took college algebra, I know that, well, this is the equation of a circle. So the trace in the plane z equals 9 is going to be a circle centered at x equals 1, y equals negative 2, with the radius of the square root of 21. So the sphere is only one type of surface called a quadratic surface. And most of the surfaces we study in Calc 3 are either going to be planes or some form of a quadratic surface. They'll make up probably the majority of the surfaces we look at. Not all, but quite a bit. And so quadratic surfaces are really just surfaces where the highest degree of any variable is 2. Now, if every exponent or every degree is 1, well, that's a plane. And a plane is not a quadratic surface. Now, quadratic surfaces are very closely related to conic sections. And it would be a good idea to review maybe a little bit of conic sections, do a little half-hour refresher if it's been a while, because, again, all these surfaces are really kind of built out of those families of conic sections. And, again, typically our surfaces are going to fall into one of 6 categories. And so this table is in your book. Again, it goes over ellipsoids, cones, elliptic paraboloids, hyperboloids, hyperbolic paraboloids, kind of in depth. And what those formulas look like. And again, it's just really useful to see, well, here's an equation, what kind of surface is being described by this equation, and kind of using this as a cheat sheet. Again, there's not a ton you can really do besides play around with it and use GeoGebra and plug it in and try to match them up and just basically get some familiarity and some comfortability with these different types of surfaces. So let's look at some of these surfaces. So let's say I want to investigate the quadratic surface in R3 given by x squared plus y squared equals 1. Now the first thing really to notice here is that although we're in 3 space, we're in R3, the surface does not have the variable z in it at all. Now what that really means is that the surface is going to look the same for any cross-section plane z equals k, or for any scalar k, and again, that means every trace is going to look the same through a cross-section of a plane z equals some value. Now, the easiest one to look at is going to be that specific trace called the projection. And again, the projection is just a trace in one of my coordinate planes. So if I'm looking at this projection in the xy plane, that's the cross-section that the surface makes with z equals 0. Again, this projection or this trace is, it's just my unit circle. It's x squared plus y squared equals 1. There's not even a z to plug my 0 into. I'm just moving from 3 dimensions to 2 dimensions. And again, hopefully we are very comfortable with the fact that x squared plus y squared is definitely going to be my unit circle. And again, it's a very good idea to sketch that 2-dimensional idea and being very careful to label my axes. Then to actually translate this to R3 means that again, that's going to look the same for every slice of z equals some number. So it's a circle all the way up, which is exactly what a cylinder is. It's circles all the way up, and it's centered along my z-axis with a radius of 1. It's a cylinder. And we probably already knew that this was a cylinder. That's a fairly common shape. But we actually have a more specific definition of a cylinder when we get to, this level of mathematics. And so if I can construct a surface by simply drawing parallel lines, that surface is a cylinder, and those parallel lines are called the rulings. And so you can see on the picture now, I've put in these blue parallel lines. Each of these parallel lines are my rulings. These vertical lines are my rulings, and because I can do this, that makes this surface a cylinder. One last example in this kind of short section. What about the quadratic surface in R3 given by z equals y squared? Well, this one is very similar to the last one in that even though we're in R3, we're only given 2 variables in my equation. In this case, we're missing the variable x, which means it's going to look the same for any trace or cross-section in the plane x equals k. So let's go with the easiest one, the projection in the yz plane. And so in the yz plane, that projection is going to be, well, a parabola. Z equals y squared is a parabola. And that looks like a very familiar parabola shape. And again, the tricky part might be recognizing how to represent this in the yz plane instead of our typical xy plane. But again, hopefully now that we see the picture, we see that it's not that different. It's that same idea. It's just reusing different letters. Same idea, different letters. In this case, y is along my horizontal axis, z is my vertical axis, but it's the same idea. And so again, for every value of x equals k, the trace is going to look exactly like this. Which means to translate to R3, it means I'm just going to repeat that parabola shape completely along my x-axis. And there it is. That's what my shape looks like. And again, feel free to actually play around with these. Like I said, search online for GeoGebra 3D Grapher and plug these in, see what they look like. But there is something interesting about this function. I can actually create the surface of this function using parallel lines, which are my rulings, which means that this surface is technically also a cylinder. Yet it's not a cylinder in the typical way that we would teach, say like a first grader what a cylinder is, but it is a cylinder in the mathematical sense because each of these rulings, well, yeah, I can use them to create this surface. All right, there's not really much else for me to tell you about Chapter 12.6. It's really just a matter of you playing around with it and getting familiar with these surfaces, what they look like, not just in their equation form, but also in 3D and playing around with the 3D grapher. And so really just take some time to explore. Make sure you spend time trying to review that chart from your book that I had also put in your notes. And if you have any questions, let me know. Have fun studying. Bye.